All right, in Chapter 7, Section 7, we're going to be looking at the leaving group and how it affects the nucleophilic substitution reaction. We will find that, that when the carbon-halogen bond breaks, it breaks heterolytically, and that means that the leaving group gets the pair of electrons. And so we will form the halide or the anion of the halogen. We'll find that the more stable that leaving group, the halide, is, the faster the reaction goes. The more stable it is, that usually tells us the less basic that anion is. So we'll find that weaker bases tend to make better leaving groups. So if we look here, if our halide is a leaving group, then the weaker this is as a base, the better it is as a leaving group. All right. And when we're looking at this in terms of periodic trends, we will find that as we move from left to right across the periodic table, basicity will decrease. So leaving group ability will increase. Now, for this to work, to look at the periodic table, we need to have the same charge in order to do a comparison based on the periodic table. So here, if we look at this, NH3 is not that great of a leaving group because it's a little bit basic. H2O is a pretty good leaving group because it is a weaker base. If we're looking at a column, we'll find that as we proceed down a column, the basicity will decrease, and so that the leaving group ability will increase. Again, in order to make this periodic table comparison, it needs to have the same charge. In this case, these are all negatively charged. So fluoride is the strongest of these bases. Chloride, bromide, and iodide are very weak bases, so we'll find that they are pretty good leaving groups, whereas fluoride is not that great of a leaving group. So most of the time when we're talking about alkyl halides for nucleophilic substitution, we exclude fluoride as a possibility. It's just not that great of a leaving group. Chloride, bromide, and iodide, though, excellent leaving groups. Now, if you want to eliminate using the periodic table as a guide, you can look at pKa. So we'll find that good leaving groups, again, good leaving groups are very weak bases, which means the conjugate acids of those bases are going to be strong acids. So the conjugate bases of strong acids tend to be good leaving groups. So here we've got chloride, bromide, iodide, and water. Those are all excellent leaving groups. If you look at their conjugate acids, HCl, HBr, HI, and hydronium, they are all fairly strong acids, very strong acids, in fact. We'll find that when we have a negative pKa for the conjugate acid of our leaving group, that's a really good sign that it is a good leaving group. Conversely, for poor leaving groups, so fluoride, hydroxide, NH2-, which is the amide ion, hydride, and carbanion, their conjugate acids are going to be much weaker than the one on the previous table or the previous page, and we'll find that the pKa of these are positive. So a positive pKa is a good sign that it's a poor leaving group, or at least that that leaving group. A positive pKa for the conjugate acid of your leaving group is an indication that the leaving group is poor. All right, so we're going to look at number 53 on the in-class assignment, and when we do, we're going to determine if things are good leaving groups entirely based on the pKa. Okay, so here we've got this one. So NH2 is our leaving group. So NH2- is the leaving group. The conjugate acid of NH2- is NH3. And then the pKa of that is going to be, and I'm just going to put conjugate acid here. So conjugate acid of our leaving group is NH3. The pKa of NH3, and I'm going to bring up this document. All right, so this document, and we'll scroll down here, and there is NH3. This is in the appendix. This is appendix that you have, that I've posted on eCampus. And if you scroll down here, NH3, it has a pKa of 38. With a pKa of 38, that means that this is not a strong acid, which means this is a lousy leaving group. So we would say, no, this reaction will not take place. Again, if your pKa is positive for the conjugate acid of your leaving group, then the reaction will not take place. Let's look at this one. Our leaving group here is iodide. That means the conjugate acid is not HA, but HI. And so for HI, we're going to scroll up. There's HI, pKa of -10. That means HI is a strong acid. That means iodide is an excellent leaving group. So yes, this reaction will occur. All right, sorry about that. I bumped my microphone. All right, so next, let's look at this one. Our leaving group here is hydroxide. The conjugate acid of hydroxide is H2O. The pKa of H2O is right here at 15.7. And at 15.7, that means that that hydroxide, this is not a strong acid. That means hydroxide is not a good leaving group. In fact, this is a really lousy leaving group. As one time I was presenting something to some professors, and I had hydroxide as a leaving group, and oh my goodness, they almost crucified me. So yeah, don't make hydroxide a good leaving. Don't make it a good leaving group, because it's not a good leaving group. All right, next here, cyanide. So our conjugate acid of cyanide is HCN, and that has a pKa, it's actually right here, of 9.1. So since that's still positive, that means this is not a strong acid. That means cyanide is not a good leaving group. So we're going to say no on that one as well. Okay, so now what we want to do is we want to go back and look at the next thing, which is the nucleophile. So in this section, we're going to be talking about what the nucleophile is, and what nucleophile do we need in order to do a particular reaction. So we'll find that nucleophiles and bases are both Lewis bases. They're both electron pair donors. The big difference is, what do they attack? All right, so the big difference is, what do they attack? Bases will attack protons, so they will react with a hydrogen, all right, and remove that hydrogen. Whereas nucleophiles attack other electron-deficient atoms, and usually we're talking about carbons, and for the purpose of this chapter, that's all we're talking about is carbons. Now, for other chapters, we could be looking at things like sulfur or other atoms that could potentially have a partial positive charge, but in this chapter, it's going to be entirely carbons. All right, so here, if we've got a halide, so carbon, an alkyl halide here, bases will attack hydrogens that are on adjacent carbons. We call these alpha hydrogens, and then here, nucleophiles will attack those carbons. So when it comes to nucleophilicity versus basicity, we're going to find that sometimes good bases are good nucleophiles, and at other times, good bases are not good nucleophiles. So it's important to learn what the difference is. So basicity is how readily an atom donates its electron pair to an H+. We're going to find that basicity is characterized by the Ka. Since Ka is an equilibrium constant value, that makes it a thermodynamic property. Nucleophilicity, on the other hand, is how readily an atom donates its electron pair to other atoms, like carbon. We will find that it is going to be characterized by the rate constant, K, the lowercase k, and that makes it a kinetic property. So there are times when we have something that's a nucleophile that potentially could be a base, and that these reactions acting as a base versus a nucleophile could be in competition with each other. And we have to just recognize when that's going to happen. I'm going to give you a set of rules to help you figure that all out. So we'll find that sometimes nucleophilicity will parallel basicity. If you have two nucleophiles with the same nucleophilic atom, the stronger base is the stronger nucleophile. For example, hydroxide is a stronger base than the acetate ion. And so hydroxide is also a stronger nucleophile because it is a stronger base. And the way that we can determine that, the pKa of the conjugate acid for hydroxide, the conjugate acid is water, has a pKa of 15.7, as we saw on that previous problem. That makes this a pretty strong base. The pKa of the conjugate acid of acetate, which is acetic acid, and I'm going to bring it up real quick. All right, so I'm going to scroll back up here. Here is acetic acid at 4.8. That means that the conjugate acid of this is a stronger acid. That means this is a weaker base. So that of course is that trend that we learned back in chapter 2. The stronger the acid, the weaker the conjugate base. All right, so stronger base. The stronger base will make the stronger nucleophile if it's the same nucleophilic atom. We'll also find that a negatively charged nucleophile is always going to be a stronger nucleophile than its conjugate acid. So hydroxide is a better nucleophile than water. This is always going to be true. As we move from left to right across a row of periodic table, we'll find that nucleophilicity increases as the basicity increases. So nucleophilicity, how good it is as a nucleophile, will increase as the basicity increases. So we'll find that fluoride is a weak base, hydroxide is a strong base, NH2- is an even stronger base, and CH3- is a crazy strong base. Well, these get more nucleophilic as we go from right to left across the periodic table. Now, one situation where basicity and nucleophilicity don't match up is when we have steric hindrance. So steric hindrance is where bulky groups make it less reactive and thus less nucleophilic. And what happens is that it slows down the rate of reaction. So here, the pKa of ethanol is 16. Its conjugate base, ethoxide, is a pretty good nucleophile. With the pKa of 16, that means this is a pretty strong base, and therefore it's also a good nucleophile. However, tert-butoxide, its conjugate acid is tert-butanol. It has a pKa of 18, which means that this is even stronger as a base, but it's not as good of a nucleophile because these methyl groups make that oxygen a little less accessible as a nucleophilic atom. So it's more difficult to arrange this particular molecule so that it can act as a nucleophile. So steric hindrance will decrease the nucleophilicity, but it does not decrease the basicity. And in fact, these alkyl groups, we will find, actually donate electron density and make that tert butoxide a stronger base. And you'll see here, this is pK 16, that's 18. You may think, well, that's not that big of a difference. Well, it is. Remember, each pKa unit is an order of magnitude. So this is 2 orders of magnitude stronger a base than this. So it is a big deal. So we will find that sterically hindered bases that are poor nucleophiles are called non-nucleophilic bases. So they are non-nucleophilic bases. And there'll be times when we want to use non-nucleophilic bases. And in fact, in the next chapter, this is going to be one of our favorite bases to use as a non-nucleophilic strong base. All right, so now we want to look at solvent effects. So substitution reactions use polar starting materials, so we need polar solvents to make them dissolve. However, there are 2 different kinds of polar solvents that we will be looking at. And those 2 different kinds of polar solvents are polar protic solvents. These are solvents that are polar but are capable of hydrogen bonding. And examples include water. This one is methanol, ethanol. This is tert butanol. And then this one is acetic acid. So these are all examples of polar protic solvents. The other examples are going to include polar aprotic solvents. These are ones that are not capable of hydrogen bonding. They are going to include acetone, acetonitrile, THF, which is tetrahydrofuran. We'll talk about it a little bit later. DMSO, a favorite solvent, DMF, dimethylformamide, hexamethylphosphoramide, or HMPA for short. Those are all examples of polar aprotic solvents. We will find which solvent you use can affect how strong of a nucleophile something is going to be. So nucleophilicity depends on the type of solvent that we use. So for polar protic solvents, something interesting happens. Polar protic solvents will solvate both cations and anions pretty well. For the salt sodium bromide in water, we'll find that the sodium is solvated by the water molecules. The partial negative charge on the oxygen is attracted to the positive charge on the sodium ion, and that is an ion-dipole interaction. So ion-dipole interaction that we've seen. We have another ion-dipole interaction here between the hydrogens on water and the bromide ion. So the sodium ions are solvated very well by the ion-dipole interactions, and the bromide ions are also solvated quite well by strong dipole interactions with the hydrogens on water. Now you'll notice here I call it hydrogen bonding-ish. Hydrogen bonding-ish. It's technically not hydrogen bonding to bromide because bromide isn't really capable of accepting hydrogen bonds. It's just too big. But that's actually kind of the point. We will find that when you have a polar protic solvent, the better this is as a base, the stronger the interaction is with that hydrogen. So again, these are examples of some polar protic solvents. There are others. Pretty much any alcohol can act as a polar protic solvent, but there are other examples as well. So nucleophilicity in polar protic solvents will affect the smaller, more electronegative anions more. They're solvated more strongly by the polar protic solvents, and that effectively shields them from reacting. So the hydrogen on that polar protic solvent interacts more strongly as it gets more basic. So fluoride has a very strong interaction with water. The chloride is less strong, the bromide is even weaker, and the iodide is a very weak interaction. That means that these, as these get less basic, they become more available to do nucleophilic reactions. So we'll find that nucleophilicity increases as the size of the anion increases, and that this is the opposite of basicity. So the small anions interact very strongly with water and end up not being very good nucleophiles. The bigger anions, they interact very weakly with the water, and so they end up being very, very effective nucleophiles. So now let's look at polar aprotic solvents. In a polar aprotic solvent, there are dipole-dipole interactions, but we don't have those hydrogen bonding-ish type interactions. So they're incapable of being hydrogen bond donors. And here are some examples. We've got acetone, acetonitrile, THF. These are all ones that I showed you a little bit earlier. DMSO, DMF, and HMPA. You'll notice all of these have polar bonds in them: carbon-oxygen, carbon-nitrogen, sulfur-oxygen. Okay, so they all have polar bonds in them, but they do not have hydrogens that are capable of hydrogen bonding. So there are no hydrogens that are covalently bonded to nitrogen, oxygen, or fluorine in any of these molecules. So that makes all of these polar aprotic solvents. Well, we will find that the anions are very poorly solvated in polar aprotic solvents. So the cations are solvated about as well as they are in polar protic solvents, but they don't solvate the anions very well. So the polar aprotic solvents are incapable of this hydrogen bonding, again, ish interaction with the anions. And therefore the anions are more reactive in polar aprotic solvents. So here, this is sodium bromide, and the solvent here is acetone. All right, so there's acetone. There is an ion dipole interaction between the oxygen on acetone and the sodium ion. However, that interaction is very weak for the anions. All right, so it's very weak for the anions, and so not solvated very well. That means the stronger your anion is as a base, the better it's going to be as a nucleophile. So we will find that nucleophilicity parallels basicity in polar aprotic solvents. So the stronger the base, the better the nucleophile. Again, you have to remember that in a polar protic solvent, it's going to be the opposite of this. And in this polar aprotic solvent, the nucleophilicity will parallel basicity. All right, and then this is sort of a wrap-up of the different kinds of nucleophiles, common nucleophiles that we will see. The negatively charged nucleophiles tend to be stronger nucleophiles than the neutral nucleophiles, so that is important. And then there's the difference between polar protic and polar aprotic. So we're going to look at number 54 and 55. All right, so okay, so what nucleophile is needed to convert A into each substitution product? Now, this is pretty easy. We just want to select what the nucleophile needs to be to replace that bromine with this. And so if the thing over here is neutral, then you're going to have a negative nucleophile. If the thing over here is positive, like it is with this one, you're going to have a neutral nucleophile. So here, this is simply going to be SCH3. So sulfur covalently bonded to CH3, and then a negative charge on that sulfur. All right, similarly here, we've got OCH3CH2 or CH32. That is the isopropoxy group. So we need the isopropoxide, OCHCH32. So an isopropoxide anion will make the nucleophile to react with that carbon. On this one, you see we made a new carbon-carbon bond, so we need our carbon to be the nucleophile. So here, there we've got that negative charge on that carbon. This is called an acetylide anion. And here you'll notice that we've got a positively charged product here. That means we needed a neutral nucleophile. And our neutral nucleophile here is CH3, 3N. There's a lone pair of electrons on that nitrogen, and that acts as the nucleophile. Since there's no hydrogen that is covalently bonded to the nitrogen, we can't just come along and deprotonate this in a next step. All right, we will look at examples like that a little bit later as well. So now we want to rank each of these in order of increasing nucleophilicity. And so we want to pay attention to each of the rules. All right, so I've got the periodic table here. We've got carbon, oxygen, nitrogen. They're all negative, so they're all negative charge. And we will find that as we go from right to left, these will get to be stronger nucleophiles. So the oxygen with a negative charge will be the weakest. The nitrogen with a negative charge will be stronger, and then the carbon with a negative charge will be even stronger. So the trend here is that the OH is the weakest, the hydroxide is the weakest, the NH2 minus is stronger, and that the CH3 minus is stronger than that. Now you may be wondering, why is the negative here on the right and there it's on the left? It's kind of arbitrary. You can put the negative on either side. All right, for this next one, we've got water, hydroxide, and SH minus. So water, hydroxide, and SH minus. And the solvent is CH3OH. Well, that is a polar protic solvent. So that's a polar protic solvent. First, let's start with the water and hydroxide. Hydroxide will be a stronger nucleophile than the water. All right, hydroxide will be a stronger nucleophile than the water. And that's the case. The conjugate base of an acid is always going to be a better nucleophile than the acid. Or you can say the conjugate acid of a nucleophile is always going to be a worse nucleophile than that original nucleophile. Either way you look at it, the one with the negative charge will be a better nucleophile than the one that is neutral. So next here we want to look at the SH minus and compare it to the OH minus. Since this is in a polar protic solvent, the polar protic solvent will interact more strongly with the smaller anion, so the smaller oxygen, and therefore it will make it not as effective of a nucleophile. So we'll find that the sulfur, the SH minus, is going to be the better nucleophile in this case. If this had been in a polar aprotic solvent, these two would be reversed. All right, so here we have CH3CH2S minus, CH3CH2O minus, and then CH3COO minus in CH3OH. So that is a polar protic solvent. And so let's go ahead and compare these two first. Again, in polar protic, we'll find that as we go down in a column, they get to be better nucleophiles. So we will find that CH3CH2O minus is not as good of a nucleophile as CH3CH2S minus. Now, where does the acetate fit in? Well, here we've got the same nucleophilic atom, which is the oxygen atom. And since that is the same nucleophilic atom, the one that is the stronger base will be the better nucleophile. Well, the pKa, and I'm going to bring up this document. All right, so the pKa of CH3OH comes out to about 16. Let's find that right here. There it is at 16. And CH3COOH, or COO minus, that is the conjugate base of acetic acid. Acetic acid is right here at 4.8. So that means that ethoxide is a stronger base than the acetate anion. So as a consequence, our acetate is going to go over here. So CH3COO minus. So again, look at the conjugate acid of these, and the stronger acids are going to have weaker conjugate bases, and those weaker conjugate bases will not be as good of a nucleophile when you have the same nucleophilic atom. All right, next, CH3NH2, CH3SH, and CH3OH in acetone. All right, so now what we want to do is we want to compare, because it is a polar aprotic solvent, we want to compare the basicity. So first, let's look at these two, CH3SH and CH3OH. Well, the CH3SH will not be as good of a nucleophile as the CH3OH, and that's because this oxygen is going to be a slightly better base than the sulfur. All right, and then the CH3NH2 is going to be a stronger base than the methanol, and so that will be an even better nucleophile. All right, so here we just want to look at the basicity. So because it is polar aprotic, it follows basicity. Next, we have hydroxide, fluoride, and chloride, and it's all in acetone. Let's start by comparing the fluoride and the chloride. So fluoride is going to be a stronger base than the chloride, and since it's a polar aprotic solvent, that means fluoride will be a better nucleophile. So the fluoride is going to be a better nucleophile than the chloride. So now let's compare the hydroxide and the fluoride. As we go from right to left across the periodic table, we will find that the bases get stronger. So hydroxide is going to be a stronger base and therefore a better nucleophile. All right, and again, that is in the polar aprotic solvent. Now we've got HS minus, F minus, and chloride in a polar protic solvent. Again, we're going to look at the fluoride and the chloride first. So fluoride versus chloride, because it's polar protic, the chloride is going to be a better nucleophile than the fluoride. All right, so because it's polar protic, chloride is a better nucleophile than the fluoride. The CH3OH interacts fairly strongly with that fluoride anion, making it not as good of a nucleophile. Now we want to compare HS minus with Cl minus. So HS minus is the same as minus SH. It's just a different way of writing it. All right, and we will find that as we go from right to left, it will get more basic. So the HS minus will be a better nucleophile than the chloride anion. All right. So there are three possible mechanisms that we can have when we're doing nucleophilic substitution. So we want to analyze those three different possible mechanisms and see see if they're all viable. And if they're all viable, then we need to determine which one is most likely to occur. So for nucleophilic substitution, we're breaking a bond and we are making a bond. All right, so we break a bond and we make a bond. And the three possibilities are that we break and make the bond at the same time. The other possibility is that we break a bond first and make a bond in the next, in the second step. And then the other possibility is that we make a bond and then we break a bond. Okay, so the order of bond breaking is what makes the three possible mechanisms possible. Likely here. And those three possibilities are concerted all at the same time. So the bond is broken at the same time that this bond is formed, that the bond breaking occurs first, and that the bond making occurs first. Turns out one of these is not very likely, and we'll get to that one here in just a moment. So let's look at the concerted mechanism first. What happens if the bond is broken at the same time that the other bond is formed? So bond making and bond breaking occur at the same time. Well, that means we're going to make a new bond between the carbon and the nucleophile simultaneously as we break the bond between carbon and our leaving group. It's all one step. Okay, so it's a one-step mechanism. We will find that the rate determining step, and since there's only one step, that one step is the rate determining step. It's bimolecular. There are two molecules involved in that step. So our rate reaction is going to be our rate equation is going to be bimolecular. In other words, it will be second order. So the rate of the reaction will depend on the concentration of the nucleophile and on the concentration of the alkyl halide. And we'll find that the reaction is second order overall, having this as the rate equation. So the rate is equal to our rate constant times the concentration of our nucleophile raised to the first power times the concentration of our alkyl halide also raised to the first power. All right, our next possibility is bond breaking first. When the bond breaking occurs first, the bond breaking occurs before the bond making. In a first step, we're going to break the bond between the carbon and the halogen, or leaving group, and that will form a carbocation. And then in a subsequent step, step 2, we will find that there will be a new bond formed between the nucleophile and the carbon. This is a two-step mechanism. We will find that the first step is rate determining. And I will show you why that is a little bit later. It all has to do with our activation energy. The activation energy of that first step is going to be much larger than the activation energy of our second step. Typically, if you're breaking bonds, that's going to have a larger activation energy than steps where you're not breaking bonds. We will find that the reaction is first order overall because the rate of the reaction only depends on the concentration of the reactants involved in the rate determining step. And that first step is rate determining. Only the alkyl halide is there. So the rate is going to be equal to K times the concentration of the alkyl halide. All right, so that is the situation where we break the bond first. All right, our third possibility is where we make the bond first. So the bond making occurs before the bond breaking. So here we're going to get a new bond between our nucleophile and carbon that will give us this intermediate, which, this doesn't look good, and we'll talk about that here in a second. And then in a second subsequent step, we're going to break the bond between carbon and the halogen, and that will give us this. Well, the problem with this mechanism is that this is not allowed. We are not allowed in period 2 to have more than 8 electrons around the central atom. So it's just not possible to extend the octet of period 2 elements. All right, so the intermediate has 10 electrons around the carbon, which violates the octet rule. And just as a reminder, it is not allowed to violate the octet rule in period 2. So this particular mechanism is not valid. It violates one of our fundamental rules about carbon. So it violates one of our fundamental rules about carbon. All right, since we're over about 40 minutes on this one, I'm going to stop this video, and we'll make the next video start with our next section looking at one of the mechanisms.